this guy. Let's say this guy is talking to this one. So these two are talking to each other. Okay, so this is for the clock, this is for the data that communicate between these two. Okay, so every time at a certain moment, you will see the data transmission direction either this way or the other way. Okay, but these two directions won't happen at the same time. Okay, so what's happening here is just like a walkie-talkie. You all use walkie-talkie previously, right? So when one person is talking, the other one cannot talk. Okay, only when this guy finishes talk, the other one can talk. So at certain moment, only one person can talk. Okay, it's different with your telephone that two people can talk at the same time. Okay, so this is what we call half duplex. So every time only one person can talk, okay? And it's a multi-master system. Means, okay, this wire, imagine is pretty long and you can have more than one masters there. Okay? So for example, this one might be the master, but you can actually connect more microprocessor onto the channel. And it's in-band addressing. Okay, so in-band addressing means, okay, let's say this guy wants to talk to this one. So before it actually send the data, it should send to the channel, okay, tell everyone who he wants to talk to. So that's always the first step, okay? Because you see whatever data you send through here, everyone has a connection there. So these guys need to know whom your master is talking to. Okay? So the first step is always the master sends the address. Let's say this guy has an address. Let's say this guy has an address 01. This one is, let's say 03. So if everyone sends this channel and know that the address is 01, this guy won't listen the rest of the data. All the others won't listen. Only this guy will pay attention and monitor what will go on the channel. So you see the address is also sent through your SDA. Okay, so this is what we call in-band addressing. In this band, okay, in-band addressing. And this low bandwidth, okay, means you have only limited number of devices you can connect. You cannot connect a lot. Okay, and I2C is usually for short distance. So the reason here is, okay, so basically whenever you add a new device to the network, you need to set your device in open drain mode. Okay, previously people asked me what is open drain. Here is the explanation. So the device can provide a strong load by pull down the network and can provide a weak high by disconnected from the bus. So can you see that you have SDA, you have SCL here. If nothing is connected to these two channels, what will you get on these two? If there's no device connected to here. If you measure here, what will be the voltage here?
5 volts.
You will get this one. Can you see that there is a pull-up circuit? Okay? So if there's nothing displayed, nothing connected here, what you will have is you only have these two wires, and this is SDA, this is SCL, and this one you have a pull-up. Okay, and this one you also have a pull-up here. Okay, this is 5 volt, this is 5 volt. So it will be something like this if no device. Right? So can you see that if you measure here, you use your multimeter to measure the voltage here, measure the voltage here, you will get 5 volt. Okay? Which means if no one is using your channel, your channels are giving you high. Okay? Then let's add in one device. Okay, how this device inform the other that he is here? The way he proved that he's here is he tried to pull down the voltage on the channel. Okay, so if no one is using it, you will measure 5 volts here. So if one device is connected to here, okay, he wants to prove that he is present, okay, he's here, so he will pull down the voltage on your channel. Okay, he will try to give you a 0 on the channel. Okay, that's why we say if this one, the device can provide a strong load, means this guy purposely pull down your channel. Okay, purposely pull down your channel, give you a load. So it's a strong load because this one intends to do that. Okay, it purposely give you a load, so it's a strong load. But if this guy doesn't want to talk, okay, so let's say if this one is talking to this one, and at that moment this guy supposed to behave like he's not existing. Okay, if he's not talking, he just pretend that he's not exist. So how to prevent this is not exist is you will actually get a disconnect. You can imagine this guy is disconnected from your channel. Okay, so if it's disconnect, if you look into this, you will see a very high impedance. Right? You will see a very high impedance means it seems like an open circuit. Nothing is there. Okay? So this means this guy can generate something like this. Okay? So it can provide a weak high. Means this guy, okay, will not do anything for a channel, but itself will behave like a very high impedance. Okay? So it's a weak high by disconnected from the bus. Basically by given a high Z, okay, impedance. This is the meaning of open drain. Okay? So you will see the example later on in the question. So in I2C, SDA is high by default, right? As I mentioned here. By default, SDA, SCL, they are all, both of them are high. Okay? And no device can force a high. Okay? You see, because all these devices, they can just give you a low or behave high impedance. Your device cannot give you a high, strong high. Strong high is given by the pull-up circuit. Okay? So no device can force a high due to open ring configuration, due to this reason. And the receiving device have to force the SDA low to show its presence. Means if this guy want to inform the other, okay, he's here, he needs to purposely pull down the channel. Get it? So that's how I2C works. Okay, so some standards, that if you consider like how many devices maximum you can connect it to the channel. Okay, since the addressing, we are using 7-bit for the address of the device. So theoretically speaking, you can get 2 to the power of 8 minus 1 this many of devices connected to here. Theoretically, okay? So all of this has different addresses. But practically, you cannot do this much. Okay? Practically, is determined by the bus capacitance, because every time when you add in a new device, it's actually introduce some capacitance. Okay, you introduce some capacitance and so on. If you add more and more devices, you introduce more and more capacitance. So what will happen if you have too much? If your capacitance becomes very big in your circuit? Why capacitance is not good? If you have a capacitor in your circuit and you give the voltage, what will happen? okay, that's the final result. Means it's an open loop, right? So when you just turn on the voltage, it starts to charge the capacitor, right? And your circuit will get stabilized after some time, right? Because the charging takes some time. And if your capacitance is very big, it takes longer time to charge it to full. Or if you disconnect, it will take longer time to discharge it, right? So the behavior on your circuit, you will see that if you have bigger and bigger capacitance, you will see your system becomes stabilized very, very slowly. Okay? Remember, our I2C is supposed to be a synchronous network. Everything, you have a clock somewhere here, and all the communications are somehow based on the clock. So if you have a big capacitance in the circuit, it's not very good. You will lose your synchronization. Okay? So this is always not very good in the circuit. So maximum, it can tolerate 400 picofarad. So more than 400 picofarad, you may get too long delay that all the communications are messed up. Okay? So in practical, if you want to calculate like how many devices you can use, you need to take care of this factor. Make sure that your total capacitance is less than this value. Okay? And another thing you need to know is, as I say, all these devices, they have different addresses, right? Let's say this one is 0, 1, this one is 0, 2, and you have others, let's say 1C. Okay? So see, in order to use these devices must have different addresses. Okay? And in I2C, these addresses are actually given by the manufacturer. Means if you buy something from the factory, even you don't connect this device onto any circuit, it has an address already. Okay? It has an address. So in order to build up your own circuit, you need to choose them purposely so that you won't have the address conflict. You don't want these two have the same address. Okay? So this is something you need to know, is hard-coded by the manufacturer, so the device needs to be chosen carefully to prevent address conflict. That's kind of a disadvantage of I2C. Okay? So this is one more page. So I2C, how the data looks like in the channel. So as I mentioned, if there's no device talking in the channel, they are all open drain mode, right? So they are all seems like very high impedance, and you can imagine they are disconnected from the channel. So if no one is talking, can you see that your channels are actually high? Okay, if no one is talking, your channels are high. So to initiate a communication, okay, you need to send a start. Okay, so master will send the start to initiate a communication. So how to indicate there is a start? The way is your master will pull down your SDA while SCL is high. So this is the characteristic for start. Okay? The devices connected to the channel, once they see the pattern like this, they know there's one master want to talk to someone. Okay? So this indicates a start. And then you are doing some data transmission between two devices. And then how to indicate a stop. How to let all the others know that this talking is finished. Is to release the SDA from low to high while your SCL is high. So this is a indicator for stop. Okay, so everyone is listening to these two signals. Okay, all the devices connected to the channel are monitoring this one and this one so that they know what's happening in the channel. Okay, and in between, someone is talking to someone. Okay, so that's the start and stop. Then during the transmission here, okay, during the transmission here, let's say, okay, it must be one master talk to one slave. Okay, the direction can be either this way or this way. Okay, means your master can give data to a device, or the master can retrieve data from a device. Okay, so both of them could happen. But before you do the real data transmission, you see your master must inform all the devices in the network that which slave he wants to communicate with. Okay, so the first thing is always send slave's address. Okay, and as I mentioned in the previous slides, the slave address is a 7-bit number. Okay, and you have additional 1 bit here to indicate, are you doing data transmission in this way or this way? Okay, so if you have, okay, so here is your slave address. If you have a 0 right after your slave address, it means your master wants to write, which means what is the direction? This one. Your master wants to write to the slave. Okay? And if the bit after slave address is 1, means your master wants to read from the slave. So the data direction is this way. Okay? So basically, by this moment, okay, the two parties are already chosen. Okay? So you already know who is talking to who. Okay, and then next you can do the data transfer. Okay, so after what I draw here, everything in blue is sent by the master. Okay, with this tool as well. Everything in green are sent by the slave. Okay, so for example here, either you write or you read, your master will send the slave address followed by a 0 or 1. Okay? Then the corresponding slave needs to respond. Okay? Response to this and to indicate that whether he is available or not. Okay? So if he is available, he will send a acknowledge. So these are green, so they are sent by the slave. So only when this acknowledge is received, you will continue the rest. Okay? So that's saying your slave is available. Then for this case, because your master wants to write, then your master starts to send the data. Okay? The data will be sent 8-bit by 8-bit. So this one will be 8-bit. This one will be 8-bit. Okay? So your master will send 8-bit to the slave. The slave will give a acknowledge, saying whether he is received or not. Okay? And once you get a positive feedback, you send another one. You get a positive feedback. And this is, look at this, P is stop. P is actually controlled by master. So master can terminate the conversation. Okay? Let's say only 16 bits your master want to send. Okay? And then let's say if your master want to read. So after that, okay, this data will be sent from your slave. Okay, because this is the data retrieved from the slave. Okay, so you read, your master is reading. Then your master will send an acknowledge, saying that, okay, I received this 8-bit. And then you send, okay, your slave will send one more. And let's say your master just want to receive 2 data. then your master will send a non-acknowledge. It's a negative feedback so that your slave won't send any more data. And then again, stop is determined by the master. Okay, so this shows how to how to write two data to the slave. This is how to receive two data from slave. Okay. So, okay, these are the same. So, can you see that? Okay, this is, after this, can you see that your master basically cannot write and read within the same transaction? Means between S and P, you can only do read or write because this is a bit. This is a bit you give. Okay? So this is a bit you give. So this determines whether this conversation or whether this transaction is read or write. Okay? So between S and P, you can either do read or write, but you cannot do both. Okay? And SCL, okay, the other channel. SCL is your clock, right? So this is what's happening on the SDA. Okay? SCL is a clock channel, is controlled by the master. Okay? It's only can control by the master. So the acknowledge, positive acknowledge, like this, this positive acknowledge is the receiver. Okay, the receiver can be master or the slave. Okay, whoever is supposed to respond is the receiver should pull your SDA to low and remain during the night clock. Why night clock? Can you see that here you have 8 bits? Yeah. So basically, this is the data on the SDA. This is the data on the SDA. Meanwhile, you have the clock signal on the SCL. Okay, you have two channels, remember? So to send 8 bits, you need 8 clocks. So this one will be sent during the ninth clock. Okay, same here. You have 7 bits here, 8 bits. This is a ninth clock. Okay, so acknowledge, positive acknowledge is whoever is supposed to respond. For example, in this way, they are the slaves. In this way, these two are this is done by the master. Okay, they're supposed to pull SDA to low and remain during your ninth clock, which means at this moment, okay, for example here, you will have SCL, you will have a clock, and SDA will remain low during this moment. So this is a positive acknowledge. Okay? And the negative acknowledge is your SDA remains high during the next clock. So if your SDA is high, okay, 1, this is a non-acknowledge. Okay? So that's some summary for I2C, okay? And let's look at the question 1. So question 1, how many I2C interfaces are used by the devices on the LPC base bar? List the SCL and SDA pins of the used I2C interfaces. So this question is talking about the actual device we are using in the lab, okay? So if you just look at the LPC 1769, okay, without talking about the base bar, okay, you can see that you actually have 3 I2C interfaces. Can you see that? You have SDA0, SDA1, SDA2. You have SCL0, 1, and 2. So basically you have 3 pairs of channels. Okay? So LPC 1769, the small bar, okay, if you look at it separately, it has 3 I2C interfaces. But during our lab, we plug our small bar onto the big bar. So some connections already done. So something already fixed. Okay? So once you plug the small board onto the big board, basically you have a bunch of devices on the base board. Okay, so the base board devices, some of them are using I2C interface, right? So this is, okay, this page is from your baseboard schematic, okay? And all the devices here are running I2C interface, are using I2C interface. So if you look at them, what do we have? You have port expander. What is this? Can you see? LED, 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 LED. So what's this? They are your LED array. Okay? So this is your LED array. So this LED array is using I2C interface. And if you look at the schematic, can you see that? The channels are here. Okay, you have SDA and SCL. And they are connected to baseboard pin PIO 0_5 and 0_4. Okay? And then look at the next one. This one is your accelerometer. Okay, accelerometer. So where are the channels? Can you see it's here? Okay? SDA, SCL. And they are still pin PIO 0504. Okay, same as your port expander. Then look at this. This is your, okay, other device that you are not using, okay, but this is a device, but this is a channel. Can you see the same pins? Okay, the last one, your light sensor. Can you see same pins? Okay, so what does it tell you? It basically tells you that when you plug your small board onto the big board, what you have is you have your LPC definitely connected here, right? And you have 4 other devices. They are connected to the same channel. They are connected to the same channels. Okay, they are using same baseboard pins, so they are using same LPC pins as well. Okay, so they are sharing the same channels. So have light sensor, accelerometer, okay, and E2 prom, okay, and you have the LED array. They are connected in this way. Okay, so although your LPC has three I2C interfaces, your baseboard devices, I2C devices, they are only using one of them. Okay, they are only using one of them. So you know this pin is, okay, let's say if this one is SDA, this one is SCL, they are PIO 0_4 and PIO 0_5, 2 of them. Okay, and you need to find the corresponding I2C pins. Okay, so this is, you know which document you need to refer to, right? The schematic, page 2, to find the pin mapping. Okay, so basically they are P0.10 and 0.11. Okay, so only one I2C interface is used by all of your baseboard I2C devices. Okay, because people design in this way. Okay, use of I2C2, so it's actually I2C2. If you look at this 2 pin, okay, if you look at this table, which is the LPC user manual, okay, so you have P0.10, P0.11 here. Can you see that they are SDA2 and SCL2? Okay, so this means the interface you are using I2C2. Okay, so you are using I2C2. So this is actually the design decision made by the baseboard manufacturer who designed the big board. Okay, because that person designed how the socket look like, how you connect your small board onto the big one. Okay? And people who designed the baseboard did that. Okay? So that's question 1. Okay, this one is easy. The second one. The second one is a very good question. I mean, if you understood this one, basically you know, I say 85% of your I2C. Okay, so details the steps involved in receiving 2 consecutive bytes from a designated slave through I2C1 interface in master receiver mode. Master receiver mode means your slave is sending data to the master. Okay? And then it's supposed to send 2 bytes. Okay? So you have 1, 2. Okay? But before that, definitely you have this one is always there. Okay? Because you need to identify the address. So basically, this is the thing. This is the whole process. Start from start bit and end stop bit. Okay. So the question is asking you how this one actually achieved. Okay. This is quite general. You send start, you send slave address, you send 1. Okay. But how it is actually gets sent out. Okay. So what registers are involved and what are the necessary bit settings? Okay, how to do this? So these are all the detailed questions talking about how to send these guys. Okay, how to send the data. So before that, let's look at what registers we have. So what's happening when you send something? Okay, when you are using I2C interface, it's like this. Okay, your LPC 1769. This is like your small board. Okay, and on it, you have your Cortex M3, the microprocessor, okay, the chip with 100 pins, okay? And then, this is the I2C interface, okay? Basically, it has 3 of them. I only draw 1 of them, okay? From question 1, you know you have 3 of them, right? I2C 0, 1, and 2. Okay, so now the question is saying, okay, you are doing I2C1. So this one is I2C1. So I draw 1 of the interface. So inside the interface, you have a bunch of registers to handle this interface. Okay? And then you have the SDA and SCL channels that communicate with other devices. Okay? So this is like your small board. Okay? So you have the registers called. Okay, so basically, if you are talking about I2C1, so you have I2C1 conset, I2C1 clear, I2C1 data, I2C1 control. Okay, you have these registers. You need to modify these registers to like do something on the I2C interface. Okay, then let me explain these registers. Okay, so you have, these are the 3 key registers. So you have I2C control set. I2C control set. Okay, so the control set register, when you write a 1, okay, when a 1 is written to 1 bit of this register, what happens is the corresponding bit in the I2C control register is set. And if you write a 0 to this register, there's no effect to the control register. Okay, so this means, okay, let's say, okay, so here I draw my control register vertically. Okay, I hope you understand this. So let's say if I write a 1 here, okay, I write a 1 in my control set register, what will happen is it will set my corresponding control register this location as 1. Okay, and let's say if you write 0 here, there will be no effect. Okay, Then let's say if I want to, instead of write 1, I don't want to write 1 here, I want to write a 0 here. How to do is you use a clear register. If you write a 1 here, basically you are writing a 0 to your control register. Okay, here is a bit similar with your GPIO set and clear, right? So set register is only doing set. Clear register is only doing 0. Okay, so these are these two registers, and you have data register. Okay, so basically this is set and clear. You write to your control register. Okay, and then you have data register. Okay, so this data register is basically has the data that you want to transmit. Okay, so you see during master or slave transmission mode, data to be transmitted is written to this register. During the master or slave receive mode, data has to be received. Data that has been received may be read from this register. So what's the meaning here is, let's say your Cortex want to send something out. Let's say this is the data transmission direction. Okay, so basically the Cortex M3 will put whatever data he wants to transmit out to this location. Okay, whatever he write here, later on will be sent out. Okay, but if let's say your data direction is the other way, your data is this way. So what's happening is the data coming in will be collected at here. So basically this guy is handling the data. No matter the data is coming into it or is going out from it, going out of it. Okay? So data register is handling the data, the actual data you want to transmit. Okay? So these are the three registers you need to understand. Okay? And then what's happening of your control register? Okay? Just now I said 1 is to write here 1, here 1 is to write here 0, right? Then why we want to write 1 and 0 here? Because this is for our control. Okay, so you have certain amount of bit here. You have 0 actually all the way to 7. These 8 bits that we can control by using this register or this register. Okay, so the 8 bits here has some meaning. Okay, it has some function. So we want to sometimes we want to write 0, sometimes we want to write 1. Okay, so the bits are actually have this meaning. Okay, so you have 1 and 0. Okay, basically they are reserved, they are not in use. Okay, so bit 2 of your control register is doing assert acknowledge flag. Okay, it is talking about the acknowledge. Just now, remember we talked about sometimes we send acknowledge, sometimes we send not acknowledge. So this bit is handling this. Okay, this particular bit, your bit 2 of your control register is handling this. Okay, and your bit 3 is handling the SI interrupt flag. Okay, I will introduce this later on in the question, how to use this. And bit 4 is handling the stop. Remember, we will send stop, your master will send stop or start. So this guy is handling the stop pattern, the stop bit, okay? And bit 5 is handling the start bit. Okay, and bit 6 is for enable the interface. Okay, so actually only this, 5 of them, very important. Okay, we use them to achieve this. Okay, so the question 2 is showing you how those bits are controlling this one. How to actually send things like this. Okay, and then let me have a start first. So I draw it here. This is what we want to achieve. This is the entire process we want to achieve. Okay, basically it's in time. Right? This is the first thing you need to do, this is the second, this is third. So it's in time. Okay? And these two are your control, the register, set register and clear register to modify your control register. Okay, so I write it here. So basically B2 is handling AA, assert, acknowledge. Okay, this one is for SI, this is for stop, this is for start, this is for enable. Okay? So what will be the step 1? Okay, even before you do the start, something needs to do before that. Okay? For example, okay, this is actually the thing how you want to use your interface. Right? So most of the time if you want to use something, I mean before you use something, you need to set it. Okay? Or like initialize it, right? So something should happen before the start bit. Okay? So the thing you need to do is basically you want to clear AA, you want to clear enable, means you want to turn it off basically. Okay? You want to clear AA, you want to another one is clear start. Okay? So you want to clear start, you want to clear enable. So basically this one is to turn the I2C interface off. Okay, you want to shut it down. You want to make some initialization, reset something. You turn it on, you want to turn it again. So you want to restart. Okay, so step 2, basically you want to set your enable. So you will turn the thing on. You see? So this is the first step, this is the second. And it's actually before your start bit consent. Okay? So how to clear the AA? Where is the AA? This one, assert, acknowledge. You don't want to assert, acknowledge, basically it means. Okay? So to clear AA, you need to use the clear register. Okay? So basically, I'm talking about your control register. Within my control register, I want my AA to be cleared, I want my start to be cleared, I want my enable to be cleared. Okay? So how to clear them? You use clear register. Right? So how to use clear register? You want to clear AA, then what should you do here for your clear register? Imagine this is your clear register. What should you put here? 1. Okay? And similarly, what should you put for your start, which is here? This is start. You want to put it 1 here. Okay? And then you want to turn enable off, so you want to put 1 here. So basically, you want your clear register equals to this one is basically 0, 1, 0, 0, 1, 1. You want your clear register like this. Okay? So basically this is the first step. Okay, 1, 1, 0, 0, 1. You want your I2C1 con clear equals this value. Okay, that is step 1. Or you can write it in other way. So in my answer, I write in this way. 1, left shift 6 times. What do we get for this one? If I shift 1 6 times to left, what do we get? 1 followed with, there's one more 0 here. What's this value? 1 0 0 0 0 0 0 with 6 zeros. Okay? And what is this value? 1 followed 5 zeros. 1 0 0 0 0 0. What is this? 1 0 0. Okay, so here your result is 100 because here you have two bits here. Okay, so you see, if I OR with them, what do I get? What I got? I will get this one. Okay, so sometimes you write in this way is much more clearer. Because for this one, I need to count 1, 2, 3. Okay, 0, 1, 2, 3, 4, 5, 6. Is it correct? Right? But if you write in this way, it's very straightforward to see. Okay, so basically this is the first step. You want to clear A, clear start, clear enable. So basically your I2C is off now. Okay, and now you are ready to turn it on. So you see why we want to turn off the start? Because when on, I want nothing is sent. I don't want to send start yet. I don't want to send acknowledge. I want to off everything. Right? Just like when you turn off your computer, you close all the windows. Right? Then you turn it off. Then you turn it down, you get a fresh start. Okay? So how to turn it on? Which register you need to modify? Set register. I2C1 const set. You want to write this location 1.
Yes.
Right? So you do 1, left shift 6. Okay? So this is step 2. Okay, so this you turn on this one. Okay? Enable your interface. Okay, so the step 1 is turn off. Okay, turn off your clear your assert knowledge, start and enable. Okay, then basically you are here. Can you see that your step 1 and 2 is something before your start. Now you are ready to send start. How to send start?
Send start.
Yeah, how? Okay, let me copy this one. Copy. Okay. So now you are somewhere, you have step 1 and 2 here already. So step 3 is doing this. Okay? So how to do this? You want to basically set your start. Right? So this is, if you want to set start, this bit is for start. Right? You want to set this one to 1. Okay, you want to set this one to 1. So how to set this one to 1? I2C1 const set. You want to this one to be 1, so you do 1 5. Okay. So this is something your processor. Okay, if you write in this way, so basically your processor tell your interface, okay, do this. Okay. Then it will take some time, you know. You ask someone to do this doesn't mean the thing is done. Okay? You need to monitor, you need to have a mechanism to monitor whether the action is done or not. Okay? So this introduces SI. Okay? So SI is a flag telling you that whether the action is done or not. Remember in the very first step, okay, so let me show you the okay, so SI is a one bit that telling you that any changes on your channel, anything happens on your channel. Okay, so basically SI is served in that purpose. So when you write something in this way, okay, this means you want someone to do, like you want someone to do something. You want to send out start, but the start is not out yet. Okay, so to let it go, you need to clear your SI. Okay, so SI is like a flag, you know, for F1, right? When you flag, the car can go, right? So this is like the flag. This start bit will not get sent until your SI get cleared. This is like tell the interface, okay, go, send. Okay? So you must have this one. So to clear this, you need to use a clear register, right? So I think all this you get the idea already. Okay? So you need to set this location as 1, means you do 1 less 3. Right? Then once you have done this, S actually goes out. Okay, start bit goes out. Then you need to, okay, you cannot imagine, okay, you can do this already. You need to make sure S is really out, on the channel already. So whether S is already finished, sent out or not, is also indicated by your SI. So SI is like a gate, When SI is clear, it's like the gate is open, SYN go out. Okay? And when the SYN goes out, this one will close automatically. Okay, it's like an auto door. So something will go past it, okay, it will take some time to let this one totally out. Right? So it will open, then it go out. Once it's finished, it will close automatically. Right? So it's working this way. SI is working in this way. So after you clear SI, you need to monitor your SI. So the next step is you need to monitor SI. Okay? See if it is set or not. Because if the SYN is totally out, it will set automatically. Okay? So this is something you want to check. How to check this one? Actually, the status, you should actually go to the control register to see, right? But actually, you can also go to the set register to see. Okay, because if you look at here, set register is also can be read. Can you see here? Set register is read and write.
Yes.
So you can either give the data to the register or you can read from the register. Okay? So to know the status of SI, you can read from set. Okay? So basically here, what you want to know is you want to check whether bit 3 of your concept is 1 or not. This is something you want to know. How to do that? This is similar like how you check your GPIO register. Remember how we check the button is pressed or not?
Use of it.
You shift the bit all the way to the bit 0 position. You end with, you bitwise with 1. Remember? Okay? So how to do that here is you do I square C conset, I square C 1 conset. This is basically giving you the entire register. Okay? And then you just want to see one of them, one bit of them, which is bit 3. How to do? Right shift 3 times. So that bit goes to the bit 0 location. You bitwise end with 0, 1. Okay? So you are checking this one. If this is a condition, if here is 1 means your S is finished. Okay? Otherwise, your S is still sending. Get it? So that's for the S. Okay? Then basically you are here now. Okay? And then so the answer here. Okay? Can you see you set the start, but the start not out yet. You need to clear the SI so that the start to move out. Okay? And then you need to wait for your SI to become 1 because this indicates that whether the previous transmission is done. Okay, so this is the way you check whether the value equal to 1 or not. Okay, so this is the way you check. Okay, so I think, okay, I think I should stop here. Okay, so basically you get the rough idea, okay? So you can continue the rest. Okay, try if you have time. Okay, we finish this in the next class. Okay, so this is a very good question. Huh? What? Okay. I mean, I also don't want to, even I have time, I don't want to finish this because if I keep talking, it's like I just deliver to you. But I want you to try the rest. Okay, you feel like you know, but you only realize you understand or not by doing it by yourself. Okay, think about the rest of the steps. Okay?
还有上午，还有上。